Okay, thanks. This morning's talk is titled 2DX Software Introduction. Obviously, Monday through Wednesday, we're doing a very fully featured introduction to how to use 2DX for processing and so on. Anji's taking a look in detail in the scripts and the MRC itself as to what's actually going on under the hood. So that kind of leaves the question of what do I talk about for 50 minutes up here. And so I think I'll do it as the following. I'm going to once again go over, I don't think we can go over this enough times, the canonical crystallographic workflow that Anji just went over, although this will be a 16-second version. I'll follow that up with some of the sort of red meat of 2DX, or maybe considering the political season, the blue meat of 2DX, where we get into some of the undocumented features that we use all the time, but I realize just aren't anywhere to be found. And can really make things a good deal faster and more robust. Some of the customization. Actually, 2DX is an extremely customizable platform, and the way that you should think about what we've written here isn't so much an image processing solution, but as more a wrapper that organizes parameters and calls programs systematically. And so what we've done by giving you scripts isn't to try to present the be-all, end-all of crystallography, but to give something that we think is an extremely good suggestion on how to do crystallography. So there's a ton of customization you can do here if you have something working in your own lab. Some optimizations that, if you're new to this, you might want to try that will give you resolution improvements and so forth. Not necessary, but as you start going into higher resolution, some good things to do. And then the undocumented features, bugs known and unknown, how to deal with them. I try and be pretty responsive on email, and I'll show you how to send things to us. I just love it whenever somebody submits a bug. I don't know, there's this sort of personal, intimate quality to it. You kind of see that people are using the software and so on. It's very easy to do that. And then I'll get into a little bit of philosophy, kind of trying to place 2DX and crystallography, I should say, crystallography as this workflow in the broader sense of what image processing is. And so I'll make a sort of a philosophical argument that we're really just another flavor of single particle, or maybe they're a different flavor of crystallography. And we're all basically doing the same thing, and maybe we'll see some obvious future directions that come out of that, at least as we see them. And then I was at this NVIDIA coding conference a little while ago, and they had this beautiful little kind of gripe session one of the days, where they had about 15 minutes. They asked people what we're doing right, what we're doing wrong. I don't know if I'll have time to get to this, but I got a little thing. Maybe later, if somebody, if I don't get time to come to this, I would love to talk to you individually and have you tell me, what you can do with 2DX that you couldn't do before, what you can't do and you'd love to, and then, some pie in the sky wishes that you'd love to see in the future. Okay, so with that, I'll go back to the sort of 16-second review of what Anji just showed. Normally, normally, we kind of intro our algorithm this way, but I did a little bit of a, hopefully a George Lucas style moment last night. I don't know how good this will be, but we'll see. Okay, so I know I use this joke every single time I introduce this, but when I started this process 3 years ago, and Henning hired me, and my first day I wandered in, 8 people are looking at computer screens that look like this. And to me, that was like the Matrix. I'm looking at this and I don't see anything. People are staring at static all day long. What's in here? Amazingly, this is actually a really good image. It's negatively stained, so of course you can actually see things. And actually, you can even see the little unit cells in here. There's one. There's one. There's one. No problem, right? Problem is, I mean, exactly. We can kind of make a story out of this. After a few years in there, you can really start seeing, the obvious crystal lattice and so on in there. But we're sort of taking advantage of the fact that 1/3 of this workshop has been about crystallization. We're relying on the fact that we have biochemical organization, which is guaranteeing us that this is the same as this, is the same as this, and so on. So we take advantage of that. We do a mathematical transform, this Fourier transform that Bob went over this morning. That is not mathematically accurate, but it's designed to give you the idea. And you can see immediately, oh, okay, there's where the information is. So in a way, this is kind of a better representation for the data that we're looking at. These spots say, okay, there's a frequency component here of a certain resolution, certain amplitude, certain phase. And when you put all of those guys together, you get yourself some kind of structure or some sort of protein, or whatever it is you've imaged that is regular. And the reason that it's a lattice is exactly what I was showing you, or talking about, is that there's some sort of repetition in your image. Just pause for a moment and comment that another way of looking at this is that the whole goal is to take these little spots of information and kind of push them all together into a coherent image. In fact, maybe a better way of looking at this is this array, if you ignore all the noise behind it, this array represents the little 64 by 64, or however many of these spots you have, picture in Fourier space of your image. So if you were to take just one little image of a protein, Fourier transform it, and then stretch it out, put a bunch of space in between, you get this exact thing. So the number of spots you have is equal, in a sense, to the number of pixels you have. Of course, it's not exactly that, because you have an angle here that isn't exactly 90 degrees, but we can think of it that way. Okay, so the way that we do our processing then is we find a little lattice, and the lattice in our process, I know I'm going a bit on about this, but the lattice in our process is the single most important piece of information that we have, and everything is being done in deference to that, so that we can get these things very precisely. We find our lattice, we mask out just those areas that we know, both that are on the lattice and also actually have a spot. There are places out here that simply don't have spots because of noise or whatever. Don't bother including those. And then we inverse Fourier transform back to real space, and we get something that looks far more like our crystal. This, again, is negatively stained, so it's very high contrast and so on. But you can, again, see these sort of poor crystal regions up here and much better crystal region down here. So you find something that looks pretty good, you cut it out, and then you use that as the reference, as Anshi said. You cross-correlate and do the whole inbending thing, find your distortions and so forth. And then, this is going to be the only mathematically accurate transform in my talk, you take your original image and you unbend it into your secondary image. This is going to be very subtle, so watch carefully. You're not even seeing anything really. Okay, that was it. So I'll just go through that very, very slowly. Really, the changes that are going to happen in here aren't even going to be noticeable to the human eye in general. But they are important. And the reason for that is that when you go back to Fourier space after that unbending process has been done, and suddenly the spots at low resolution are far, far more well resolved. And I don't know if you can see this with the lights, but the spots at higher resolution, which simply weren't there before, are now showing up. Are those noise or signal? Well, that's debatable for later, but the point is that you see a much more clear lattice. And more spots means more pixels, more information in the final image. And with that, you can very carefully extract each of these individual amplitudes and phases, push them together, and come up with a final coherent image that actually looks something hopefully vaguely like your original protein. So that's my 16 seconds of crystallography. I'll just show you that again. It took a while to make. Okay, so there we go. Okay, so now the question, the rather important one: how do we do that? Actually, the MRC package is beautiful for it. There's a mountain of publications that sits on top of the MRC suite, and there's really no reason to, I mean, in our opinion, in our kind of processing context, we really don't see any reason to sort of change that too much. What can be quite difficult for grad students is sitting down, even though most labs have some sort of canonical scripting written by someone, it can be a little difficult or daunting for a grad student to, day one, be given a crystallography project and someone says, please read through this and start working. There are parameters that you really want to keep track of, and most importantly, that even as you're going on, even as you're processing these things, if you want to suddenly make massive changes to system-wide parameters or images or what have you, any kind of conditions, you really do have to kind of carefully go through this again. And so again, 2DX is trying to step in not so much as an image processing platform as such, but more a way of keeping track of everything and allowing you to experiment more effectively. That said, most people do have these scripts in their lab, and so the first thing we were finding when we were developing this was 2DX is great, it looks pretty, but we already have our stuff and it works fine. And I agree. You know, if you've got things that are already fine-tuned for your projects, there's no reason to jump away from that. I know that in the Mitsuoka lab, for instance, Kaoru goes back and sort of redefines the set of scripts for each individual project that he starts. And that's really kind of the right way, in my opinion, to go about things. I mean, you really should fine-tune. But that said, we wanted to be able to just take advantage of that, and so that's really what we've done. And I'll take you through that a bit here in a moment. By coming up with a very, we hope, minimal, intuitive-ish set of little flags that you can add to your C shell scripts that exist already. We're adding bash and in principle Perl or anything else. If there are any major requests for types of scripts that you run, we're happy to introduce those. But in any case, all of these little things that you see up here end up going into generating the full UI that you see that is 2DX. And so really there's nothing in particular special about the graphical user interface that you're usually seeing, except insofar that it's been defined in the scripts. I think for me, one of the best parts of this project, the most enjoyable so far, was last time, 2006. Anchi and I were talking about, I guess it was either diffraction processing or something else, and you were asking if it would be possible to put it into 2DX. You had a script, you quickly wrote something, and we managed to get something that was at least running formally on here. And that's kind of my dream, is that if you guys have something that is already working, please give some thought or an attempt to actually writing up a script and see how far you get. So I'll just take you through some of the mechanics, some of the important keywords, and so on. These are documented in principle, but they're not documented very well. I appreciate that, and you know, if there's anything that you guys come across that you really want to do, please email us, or better yet, edit the wiki that we have. I'll show you what that is in a moment. So just to give you an example, let's look at our refined script. Again, if you want some more detailed information about the layout here, what we're actually doing, please do come today to our last session on 2DX. Friday we'll be doing the 3D merging and so forth, where we'll get into more detail. What you see here in the standard scripts, though, is a little drop-down menu next to each of these guys. Now, these are populated individually from your install location. Okay, so when you install 2DX for the first time, you're going to have, wherever you've installed it, just ignore this first bit, inside of there's going to be a little thing called kernel, and inside of kernel there'll be a 2DX image and a 2DX merge directory. And inside of each of those there's going to be some script standards and some scripts custom. So if we just go ahead and look at those, everything you see in this directory, 2DX apply ctf.script, etc., is used in generating everything that you see here. It just automatically opens that folder, goes through, adds all of these scripts individually. So let's see if we can find refine lattice right here. So that was just drawn right out of there. And then it was used in all the parameters that you see, really all the images, if you were to see any here, or results that are generated, all come from this script. So let's go ahead and have a look at that. Okay, so main goal is a template should be by itself an executable C shell script. I mean, in principle, if you were to run it, it might crash because it doesn't have certain variables defined in the right places, but formally it should go start to finish. So most important thing, if you want it to show up in the viewer, just give it a little hash mark and then a title. Most of our flags are defined this way: hash, and then some keyword, colon, and then what have you. It's vaguely like XML. We really struggled with maybe should we use XML or some other thing. In the end, it seemed like that was just slightly more complex than we really needed, so we went with these. Next one, sort order. You notice that these standard scripts appear in a particular sequence. And that's really just controlled by a number that's between 0 and 100 that we just put in here. 32 just as it comes after whatever 30 was and so forth. Manual. This is a flag that is on a line-by-line basis interpreted as HTML. So this is a fully featured HTML browser that we've got in here. So for instance, on this guy, you can see some text, and that's exactly the same thing that was written here at the top. These can get far more complicated than that. For instance, in our initialization, we've got links that will open our local browser. We even have images in here as well. So really anything that you can do with maybe the exception of Flash or some other fanciness, you can do there in the manual section. And this was so that people our kind of dream about this is that as people start generating these things, if someone wants to take on helical processing, for instance, which we'd very much like to do, and they write a script for it, please upload it, assuming that you want to, and the manual will hopefully help explain things in a way that online documentation might not. Okay, the next thing are these little global variables, and all of these represent parameters that are drawn from a common database, and this is defined here in, again, there's this kernel directory in your local 2DX install, and in there's a config directory full of all kinds of interesting things which control the behavior of 2DX. The most important one here being the 2DX master.cfg. So every variable that you might want to use that is commonly available to every script is going to show up here. And I don't know if I have time to go over what each of these things does, but in general, there's a label, there's a little legend that explains if you were to go into 2DX and right-click on one of these variables, much of what you see here is going to be defined in fact, all of what you see is going to be defined in the configuration file. Most of them aren't actually necessary in defining a parameter, but they're quite nice. There's even a link to where you can go for more help if you like. There are a couple of other things. The help, as you see, the type, I can't go into all the types that we've got, but look through this config file and you'll get a sampling of everything that's available. Whether it's lockable, meaning can you tell it to a lock when you see it in 2DX basically says nothing, not the user, not even a script can update these values. So for instance, we had just determined, say, a real unit cell, and we never wanted that touched again. We could block that, and neither a user nor the scripts could then go in. And that's, again, all there in the configuration file. We've got inheritable upon init and sync with upper level. This basically says when you import a project using 2DX merge, does this variable automatically get populated from the master configuration in the merge project, or does it get initialized from this global configuration? There's a sync with upper level that basically says some variables just don't change. You usually have a project-wide symmetry, for instance. You never want that to change on an image-by-image or even tilt range-by-tilt range basis. So this just allows you to define variables at one place and never again. And then we've got this little way of kind of hiding data. If there are some values that are just distracting to most people and you really don't ever change them, you can label them as advanced. And we've got this little advanced/simple view. And there are a few, you can see them listed here in italics that are described. Again, it's up to you as to whether that's important or not. And then finally, we've got the unique identifier for what the variable is called in the scripts themselves, and then what it's equal to. Again, C shell. If you were to just run this thing, it would define all of these variables, and you'd be done with it. So, going back to here. Okay, so we've defined our globals. Basically, if you do this global tag and then the variable name, that unique identifier at the bottom, then what will happen is you go into 2DX, and so for instance, let's just pay attention to one of these, tilt axis, for instance. You go into 2DX, when it loads up for the first time, you see that tilt axis is in here. In fact, all of these parameters are listed here. You don't have to do it this way. You can actually do some what are known as regular expressions. If you wanted to do, everything starting with the capital letter P, followed by a letter, followed by a 4 or something like that. It would include all variables of that type. You can also do kind of wildcards, just include everything. We do that, for instance, in our all parameters custom script down here. If you just click on that, every possible parameter is available in this custom scripts area. Okay, so when you're done with that, you just put this little flag and local vars. You can actually define variables in this script in exactly the way you did in that master config. So if you've got a flag or something else that's not really appropriate for the global configuration, or if you're sending a script to someone else and you want to make sure that there is something in there, you can actually define your variables in here. When you're done with that, you end your local variables. And then we've got two specially defined directories. One's bin_2dx, one's proc_2dx. Those will get populated when you run, just using this play button, with the bin directory, the MRC or our 2DX MRC directory is, and the prop directory where we keep a number of sort of useful scripts for output and display. So that way you can just do a $hash, $bin2dx / whatever your name of your program is and just get right to it. All of these other variables are the ones that are available to the script. So if, for instance, we were to say set tilt axis equals blank, this represents a template. So it copies the template to your local image processing directory, fills in all of these empty quotes with the appropriate value from 2DX, and then they're defined when you run the script to the remainder of the execution. So again, this is really sort of standard shell scripting stuff. It's hopefully not too complicated, or at least not much more complicated than the scripts that exist already. Beyond that, we have a few little semaphores like evaluate, which doesn't do anything anymore. I should take that out. Progress, this little progress bar that you see up here at the top of the screen, if I were to just do something simple like calculate an FFT, you can see that that's just marching across diligently. That's totally controlled by the script. So if you've got something that goes and re-refines a few times, you could, in principle, march up to here, go up to here, back forward, and so on, and then finally finish up there. Again, all completely script controlled. And basically what's happening is 2DX is just sitting outside listening to the output of this program. And anytime a flag is thrown out, it automatically rips that out and interprets it as a command. There is a couple more things in here though. When you have, for instance, changed something, in this case refined lattice is actually taking the input lattice and then doing something to it, in this case using mmlatref, and then putting it into your refined lattice. So what we do is we echo set lattice equals to whatever your new value is, and we echo that out to the logs directory / the name of our script, which in this case is 2dx_refined lattice. We just defined it as a variable, .results. And so 2dx sits there also monitoring the directory, the logs directory, and also monitoring these files. And as soon as they're created, they're parsed. And if they find anything that says set blah equals blah, then they show up here in the results. And so you can see after calculating FFT, there are two values that were changed. That was all in this log file and just automatically interpreted. Same thing with the images. If you look through the scripts here, I'm sure we must have something. Yeah, no. Anyway, somewhere in here, I'm sure there's an image block. Maybe it's better to look in that because it is rather central. Okay, well, in any case, there is a way to echo out images to okay, well, oh, there we go. Okay. So basically, you echo # image : the name and the location of your image in quotes, and then in these little angle brackets, if you want to put in something that appears. You see here in 2DX image, for instance, we've got image, histogram, FFT of image. Obviously, we haven't called those values image, and be done with it. It's actually called something a bit more complicated in this case. Look over here, actually, you can see that these names are all extremely complicated, kind of hard to remember. And so what we've done is we've just replaced those values with these little nicknames. And then you just echo that line out to this same results file again. It's processed automatically, and these guys just show up as they're added. And so this has hopefully the virtue of, you can just see as it's going, it's just one by one adding these guys. It's all automatic. You don't have to do anything more than just echo out to that file. Okay. I guess I'm finished at 11:20. Is that right? 25. Okay. So maybe I go into a couple, just a few more secrets here, and then I'll get back to some of the philosophy of what 2DX is. One of the major undocumented features that we've got in here is in the main directory. You can see, let me just close this, it's a little less cluttered. There are a bunch of directories, some important, some not so, to what you want to do, but we do have this plugins directory. And if you look in there, there's a soon-to-be-useful tools directory, not too much in there yet. And then there's a translators directory, and this one is useful at the moment, at least in 2DX merge. It occurs to me that this might not be in 2DX image yet, but it's easy enough to put in there. If you put a 3-letter name representing a particular extension of a file, followed by a .tr, this directory is parsed whenever you double-click on a file over here in 2DX. So for instance, if I were to double-click on, hopefully, histogram, it's going to automatically launch our PostScript viewer, bring it up, look at it. Okay, that's a default behavior. If, however, you have some other thing you want to do, for instance, MTZ files are compressed data that you oftentimes want to look at in an HTML browser, then what you can do is add a mtz.tr, and have a look at that. And what you can see there is basically whenever an MTZ extension file is double-clicked, it runs this script. And it takes advantage of one reserved word, which is going to be down here at the bottom, which is application name underscore 2dx underscore app, and then the out file. And the out file is whatever you define here. So basically what this does is it uncompresses our MTZ, does a few things in terms of formatting, and then uses the web browser to open it up. And the web browser is defined, again, here. You have in your home directory, tilde.2dx, we sort of secretly create a little configuration directory in your home directory, .2dx /2dx.cfg. And this is a major undocumented feature that most people don't know about. It's actually really important, and we need to get it up there. This is the thing that defines how 2dx actually opens links and views postscripts and opens these scripts here when you double click on them. And also recently we've included a 3D viewer because the 3D merger, as you'll see on Friday, is now fully capable of 3D model viewing. So all of these things are available. If you define something else in here, you have access to that also in the translator. So a lot of customization there available. Do check here though. If for some reason something's not happening, you're double clicking on your PS file and it's not showing up, it's probably because of this. And I want to write something that actually just is graphical and you just change it to whatever you want. Haven't gotten around to that just yet. Maybe one more set of little secrets. I mean, there are quite a few of them, so please come up and assault me with your questions as you see me during the next few days. One thing, for instance, we've recently added is there's a tilt indicator. Obviously, this isn't too interesting because there's a default 0 tilt, but you can actually see the tilt axis in both Fourier space and real space in all of these images. For instance, in addition, you could show your lattice and view Miller indices. It's another thing that doesn't show up too much. I mean, some people don't know about this. It's kind of interesting. One I added a while ago was this screenshot ability. This takes a fully qualified screenshot of the entire viewable region, not just the viewable on the screen, but the entire image, and saves it to screenshot.png in your home directory. Might be slightly different on Linux, maybe saves it to a TIFF or so. You can also view the taxa. One thing I'm not sure everybody's aware of, or even necessarily would care if they were, we have the ability to view a fully qualified Fourier space. And that basically maps each pixel value, as Bob was saying, you've got your amplitudes and phases here. It maps each pixel value to an amplitude, that's the brightness or intensity of what you see, and also a phase, which you can see is kind of rotating down there on the right in the phase view, is just mapped to the standard Roy G. Biv hue there. And so it's cyclic, so 0 and 360 should have the same color, and so you can see some neat things. Like for instance, you can see phase coherence, or maybe lack thereof, in these cases a little bit. And so the more centered your references are, and the more closer to the phase origin you have, these things will start looking prettier. For helical processing, this is really quite useful. We don't do that yet, but this feature is in there. Okay. Last thing, I'm really proud of this, and it's absolutely useless at the moment. I had someone who said that loading these images was too slow. Loading an 8K by 8K image was taking 30 seconds, 45 seconds or so, and that was unacceptable. I looked at that and said, you're right, we can do better than that. I've used Google Earth. There's no reason that we can't load any image in basically constant time. And so basically that's what I've done, is I've added this block loader which loads in just the section of the screen that you want to see. And so you can see the little black regions that suddenly are kind of being loaded in. Once they're in, they're just thrown into a permanent fixmap cache, and so you can just very quickly move there. And so this loads very quickly over the network and so on. It allows extremely quick zooming, so you don't have to worry about that so much. If you zoom out, you can start seeing those areas that weren't loaded in and so forth. It doesn't do anything besides this. So at the moment, it's just a really fast image viewer. If you got a big 14K by 14K, you want to get a quick thumbnail view of it, that's a gigantic thumbnail, then this is the place to go. I'm trying very hard not to screw this up, to use a technical term. So I want any tools that I add here to be very user configurable and very dynamic, extensible, and so on. And I'm thinking very cautiously about how I want to do that. So I expect to see this where the real development of the image process, the image visualization end of things is. At the moment, this is where we're at, though. Other nice thing is that this pixmap cache is saved in memory. So if I just double click on that guy again, all of those images are still in there, and this is sort of rotating 2 gig file that things get swapped out and then swapped back in as they're needed. Okay, so those are most of the secrets that I'd kind of like to go to at the moment. There is just one last point I'd like to make. See this little Safari-like bug down here at the bottom? Please use that. Anytime you find anything in 2DX that doesn't work the way you'd like it to or should, you click that. It takes you straight to our 2dx.org page. Gives you a little bug submission tool. You can add a title, a description, classify it as a bug, or it doesn't have to be a complaint. It can be also a feature, or a, hey, I got 2DX to do this, and I shouldn't be able to, but it's still useful, that kind of thing. You can select your topic and so on. We've got maximum likelihood in the MRC version. You can assign it to Henning or I, but we'll just assign it to where we want. Okay, so I'll just go ahead and get back to it with my last few minutes here. So now I'd like to kind of digress into a bit of philosophy as to the future of what I view as the future of crystallography and its place in the broader world of image processing. And I'll go over some future directions about where we're going to be going with 2DX development and also methods development and all that. And then some practical applications that should be able to be running very quickly. One is the reconstruction workflow. Okay, this is again the workflow I showed at the beginning and actually went into in great detail of find your lattice and so on, generate your model, CTF correct, refine. Use that refined model to go back to the cross correlation. Well, if I put up right next to it a single particle workflow, pick your particles, CTF correct, find your Euler angles, average, embed in Fourier space, produce a 3D reconstruction, refine, start over. Completely different in every way, except, in my opinion, they're identical. In a sense, we're using the fact that we have the most powerful tool, namely our biochemical alignment, which is represented in Fourier space as a lattice, to do almost all of this in a go. And so if we kind of look at it from that perspective, we start seeing some patterns emerge that maybe we can take advantage of. For instance, picking particles is nothing more than using that initial Fourier filtered model for cross-correlation and then unbending. There's no mathematical difference between Fourier filtering and averaging. They're exactly the same thing. So what we've done is we basically said, okay, we've got most of our image in the right place, but some are not. So let's try and push those to where they should be, get them to line up in line, and then they can participate in this group Fourier averaging. So we've kind of sidestepped the particle picking, but as we described, and we'll probably go over in the maximum likelihood talk, you can use the profile, which generates positions, in single particle processing or in maximum likelihood or so on, as a single particle project from here on out. Determining tilt geometry. Again, this is the problem in single particle. It's not really, I don't want to say it's not a problem for us, but it's not really a problem for us. We usually know what it looks like in the microscope, and if we don't, we have both the lattice and the CTF and a number of other things that we can just jump onto. So again, it goes back to knowing that biochemical arrangement. Getting an accurate phase and amplitude. Again, this is that Fourier filtering exactly the same as averaging in real space. Generating a model is identical. In fact, once you've got your model, you're really basically doing the same sorts of things. And this is where the experience of the crystallographers and single particle folks just overlaps completely. And that's why we can all use the same tools past a certain point. That's why Spider is useful to so many people. Refining is really identical here also in the sense that we we generate a model, we go back and we use that to refine particle picking, the lattice finding, that kind of thing. You know, all of these, well, actually we don't refine the lattice, but in any case, it's very similar to the refinement in the workflow. So you could, in principle, think about what is it we're actually trying to solve here. We're trying to find our particles, we're trying to do CTF determination and correction, assign some Euler angles, it's not actually really a problem in our case, and then average appropriately, embed in Fourier space appropriately, and then reconstruct with a mask. And I'll just go over just a couple of quick applications. In Hans's group, Phil Cook is working on single particle sort of study of crystallographic data. And so what he did was he extracted exactly as we talked about using the profile, pulled out all of the individual unit cells, and then threw them through EMAN and got an angular distribution of where these guys were in Euler space, and he found that there was actually a significant distribution of angles. That when you look at a flattened image, oftentimes there can be as much as a 15-degree out of plane rotation for these guys. So this is an example of a really interesting and promising use of kind of these hybrid methods. One we're working on is maximum likelihood. I say nothing more than just showing you this slide, since Henning will be going over this. But again, we're doing something similar, where we're trying to take advantage of the fact that we know where the particles are, and we know a lot of other data about them. Can we in either real space or Fourier space, apply mathematical tools that finally give us a better math? I'll let Henning talk about that more. That I'm free to discuss afterwards a bit more about the philosophy, but I really encourage people to think about that. Ben was asking me if we're looking at sort of local rotations and rotationally unbending an image and so forth. I would submit that a rotational unbend is really just another flavor of a single particle-like process or procedure that you can do on crystallographic data. And I would like to see that much more. I think there are sort of continuous transformations that aren't necessarily Fourier, promising among them the fractional Fourier or wavelets or so on, that can do similar sort of aspects in this workflow, that can kind of pick up the slack for poorly ordered crystals. Final comment on that. If you look at a biochemically arranged data set and it diffracts out to 1 angstrom, and you take all of those, and all the unit cells in rotationally misalignment by 15 degrees or so, it will no longer diffract out to 1 angstrom. But the information is still in there. So we can get at it. I mean, in principle, there's no physical reason that we can't extract that. So I think that's the direction that we're going to be thinking in future. You may or may not agree, but we can talk about that. Parallelization, all the computers in the world are just blowing up in terms of numbers of processors. We've sort of reached the peaks of where we can go, and now we're kind of spreading out under the plane. Processors are as fast as they're likely to kind of get in the next few years without quantum computing or something. And so, for instance, the NVIDIA group is making these increasingly large graphics cards, which originally were used for gaming or rendering CAD and CAM things, now for research scientists. And the recent one is the Tesla, which actually doesn't even have a graphics out port. It's just a massive bank of 256 processors with 4 gigs of RAM. And these things are blazingly fast. They can increase your programs by, in some cases, 500-fold. Now, that's not just some sales pitch. I mean, I've actually seen that in these things. Typically, it's going to be more like 20 to 100-fold, but still, that's not a small improvement. So most of what we write now is kind of being geared more towards this schema. Do you need a Tesla or an NVIDIA graphics card? Of course not. We're writing it so that it just takes advantage of multiple processors. Visualization is a big one for me. As I said, the view that you saw there, the block loader, I'd like that to be just kind of the beginning as we go forward with certain developments in 2DX. A lot of tools out there that I think are really badly needed. One is a lattice line sort of interaction, being able to look at how these lattice lines are fit, throw out outliers, that kind of thing. I think that getting a more visceral feel for where that, what your lattice lines are looking like, if nothing else, would help guide your project. Being able to edit them would be a definite bonus, but maybe once you talk some more about those sorts of things. So there's just a few images of visualization. Practical applications, the 2 biggest ones that I get asked for in 2DX is when are you going to have diffraction processing, followed immediately by when are you going to do helical processing. And the first answer is hopefully pretty soon. Diffraction processing is on our front burner. We're still thinking about how best to do that, but we're open to suggestions, and And it's definitely going to happen. P-level processing, I don't know. I don't know anything about it. If there's somebody else out there who knows a lot about it and wants to collaborate, I think we'd be very happy to look into that. With that, I will thank all of the many, many, many people that are involved in this project, including the people that pay my salary, NSF and NIH. And just a final plug, Fern is unfortunately not here, but I just wanted to thank the two labs that I spend the most time in, because really it's the support of the community that keeps these things going. So with that, I will thank you and ask if there are any questions.
How do you run updates of the software?
Well, at the moment, we have a little update available button that when there is an update available, there'll be an annoying little window that pops up saying you should upgrade to the most recent version. You can also go up to this little update thing under options. Is it as easy to use as, say, Ubuntu's little package updater? Okay. Oh, sorry, you're right. Okay, so if you go up to, okay, so if you go up to options and update, then you can see what the most current version is. You can see that the one that you've got is the most current version. We've got all the changes and everything. When you click this update button, it's going to actually take you to our web page, and there'll be an installer. Apologize for that. We actually have separated out the scripts and the internal programs in such a way that those can be installed on top of an existing 2DX installation. At least it will be in the next version. Because at this point, the overall layout and everything doesn't really change from version to version, and there's no real reason for you to have to re-download that and so on. So, almost. Ease of upgrade is still an issue. Okay, so just a final point. I would have loved to have asked you guys some questions about this. I see that I'm very out of time, but maybe sometime later in the evening or so, if you guys want to approach me and say, hey, I love 2DX because I can do this. I can't do this, and I really wish I could. And can 2DX process and crystallize my things for me? Other sort of wishes that you'd love to see that maybe we can do. So with that, thank you.